again, guys, thank you very much for joining us. And I think this will be a great topic, like Brian said. And I really like talking to you all before and excited to hear more in-depth talk. But we're glad to have everybody here tonight at Pone School. Thanks for showing up on a little bit of a different night. We switched it up a little bit just to work with scheduling. But we're excited you're all here. Hope we have a great night. Hope we have lots of great questions. But I want to pass it over to Dr. Saumitra and Dr. A presenting on demystifying deep learning. And I'll jump in with Q&A when I feel it's appropriate, or if they take a little stopping point, I'll ask any questions we may still have open. But over to you guys. Thank you very much. It's all yours.
Sure. Thanks, Sheldon. Great to be here to talk with you guys about this, get some feedback, answer some questions. It's always fun to engage. Can you guys hear me okay? Everyone okay? Sheldon, can you guys hear me okay? Just making sure.
Yes, sorry.
Okay, great.
I'm muted. You sound great.
Got it. Okay. Yeah, so we're from Blue Hexagon. It's a company I started like 2.5, 3 years ago. Before that, Ali and I both actually worked at Qualcomm. If you don't know a lot about Qualcomm, it's where most of the 5G and cell phone chips are made, and now IoT and cars. So we worked a lot on platform security, and also looking at how to secure the network itself, like fake base stations. In Washington, D.C., if you go around there, there'll be tons of things pretending to be AT&T, but they're all from the foreign embassies trying to hack your phones, for example. So how do you detect those kinds of things? We worked with Homeland Security a lot on projects like that. Prior to that, my background is that I was at US CERT at Carnegie Mellon long time ago, when machine learning was something of a toy. You took a single PCAP and tried to do some funny fun things with it. And I've seen it over the last 20 years, grow in terms of what it can achieve. And that's what I wanted to give a perspective today in this talk. Both Ali and I worked on this in different parts of applying machine learning, not just for security, but speech recognition, voice recognition, even, for example, at Qualcomm, we used it to figure out how to maximize given a chip area, how do you put the chip onto the wafer by reducing the amount of space you need for the circuit. So there are lots of very interesting applications for AI and deep learning, and we'll discuss all those kinds of things, followed by looking at how it applies to security. So the agenda, we're going to start from some real-world examples of deep learning in action, so you get a feel for what kind of things it can do at a very high level, and then we'll look into how is it able to do that, why it works, what's the fundamentals behind it, and how did it evolve. This is not something that just came out. People have been trying to do this since the 1940s in some form or the other. And why is it that only now we see these interesting applications? So we'll talk about that. We'll also touch on when it doesn't work, right? So it's anything probabilistic like machine learning or deep learning. It's always trying to predict things. When you predict things, you make mistakes. Right? That's always a part of prediction. But if you're mostly correct and you make very few mistakes, it becomes a very useful tool. So it's important to know how to tell snake oil from reasonable claims. And actually in security, you'll find there's a lot of these kinds of claims, 100%, 0% mistakes, and all these kinds of things are, I hope you'll get a perspective on how to question these kinds of claims and what's realistic, what makes sense. And finally, we'll talk about, deep learning and cybersecurity, so it's more, how to take all these technologies and apply to some specific problems we're looking at. Okay, with that, I want to start with a few real world examples. The first one is from the medical field, and I'll go across media, speech, and all kinds of different areas. You get a real sense of what kind of things a deep learning AI model can actually achieve. So let's start with this first application of deep learning
There's no cancer treated without understanding what the pathology is.
The tissue slides that pathologists use to diagnose cancer contain a vast amount of information. It's very time-consuming, very fatiguing.
Every cell needs to be examined. Sometimes cancer is very difficult to recognize.
We had the idea for the microscope project about a year ago. It brings augmented reality into an existing microscope to detect cancers in real time. We're bringing AI directly to the user and meeting them where they are right now.
I think this is going to enable almost all pathologists to have access to machine learning.
Just a few weeks ago, we got it working end-to-end.
It has a camera, so it's seeing the same thing I'm seeing. Information is being fed into a computer, which is doing billions of calculations and telling me that's the tumor, that's not the tumor.
Right now, it detects breast cancer and prostate cancer, but it could also work on any other cancer type that we train models for. The knowledge that you're getting when the microscope points out cancer to you is the knowledge of many pathologists who contributed to training the machine learning model.
We had a team of pathologists that went through thousands of images, teaching the computer what cancer cells look like.
I think it has been very effective at locating areas of concern. It's like getting a second opinion.
It's going to make the doctors much quicker. They're going to make them better, which is going to overall benefit the patient.
The mission is to increase the accuracy and availability of cancer diagnosis and save people's lives. I can hardly think of anything that's more motivating.
I guess, if you guys, could you all hear that? Did it come through the audio? Just want to make sure.
Yep, sounded great.
Right. So this is a very interesting, so you can see, there are many parallels to what one would do with this in security or other fields. You have the domain experts. Who are they? They're the pathologists. They are the ones who are dealing with threats, let's say, which are like cancer, right? And now they have, we're building AI tools that help them in the sense that they can take the knowledge of many domain experts. So it's almost like the model has been trained with, let's say, 1,000 pathologists who have labeled the data and taught the AI what looks like a tumor and what is not a tumor. And then you bring that technology to bear in a new case. So you have a new case coming in, it's not been seen by the AI before or by the domain expert, the pathologist. And this tool is then looking at those images and it's basically classifying what it thinks is a tumor or not. So it's not saying that I'm just going to trust it blindly, but it's giving suggestions based on all the past data that's looked at. And computers can look at, and what deep learning does is it learns from data. So it can look at vastly more data. If you have one human pathologist, I mean, it can't go through a million different CT scans. It's impossible, right? They rely on intuition and learned knowledge. Whereas a computer can actually see all the possible variations of something, something bad, which is, it could be a tumor, it could be a malware. So that's the key insight I want you guys to take away, that what deep learning does is it looks at the past, looks at samples that have been labeled by domain experts, and then forms an opinion of anything new that is given to it based on the past knowledge. Right? And that's really what machine learning is doing. So this is one example, a very compelling example. When I was at Carnegie Mellon in, this was 2001, we were using very simple ML to find glaucoma in retinal scans. So if you take a retina and you scan, it's very hard for doctors to make a lot of mistakes because it's very subtle. The glaucoma is very subtle, but the computer could pick it out. And that was the very first, few applications of machine learning. And that time we couldn't do things like this. And now you can actually take entire CT scans or X-rays and predict, what's happening. In fact, just earlier this year, you had the FDA actually authorize the first AI in an ER. It's used for diagnosing pneumothorax, so collapsed lung. And these things are very notorious. The doctors don't realize it right away, and it can be fatal. So they authorized a machine to be able to look at a quick scan and just make the determination, so the ER can prioritize who goes where. So this is an example of real uses of this technology that's happening just in 2020, where it's becoming reliable enough. There was always toy examples in the past where I could, take some pictures and show, hey, it works for these 5 things. But if you go to a real hospital and start using it, it makes a lot of mistakes, right? So that was the main issue. And now we're getting to the point that it becomes usable, means it's mostly right and makes very few mistakes. And that's where all AI needs to evolve so that you can trust and use it. So this is one example. Let's look at another one. For this one, I'll not play the video. This is basically looking at computer vision and trying to understand the world, right? If you look at Tesla, self-driving cars, or even your cell phone, it's basically able to understand the world and put it in context. So here, sorry, I went back in time. Turn off the video here. So what this is showing is, it's a camera. It's getting all this pixel data in real time, is looking at the pixels and trying to diagnose or sort of predict what these things are. So not only can it tell it's a person, it's also a person wearing a blue jacket who's standing. And this is important because it's not enough to just say it's a person if you're driving a car. Most of the latest self-driving cars need to predict if this person is walking and might come in the path of the car. So not only do you need to detect person, you need to detect intent or potential future intent, right? So the context of what is about to happen is also important. And that's what deep learning can do. Not only can it first can find what's a face, it can find here's a person, it can look at cars, what vegetation, and all of these at the same time in real time. The question, and that's another interesting aspect here, real time, right? You can always have analytics, like think of it like your sim. you get data and you go back later and you analyze it, find correlations. But many times it's too late. For things like this, you need to know right away. I can't come back after 10 minutes and figure out there's a biker here and I might hit it, right? So you need to make decisions in real time. And that's another thing that deep learning allows. It allows you to do things in real time that are very accurate, right? And this is critical if you look at what the autonomous cars are trying to get to. They're trying to get to level 5 autonomy, where you can drive them in city streets, right? And it's a very hard problem to solve. You need to have the computer be able to classify and understand all these things as they're happening in real time. So if you look at the first video we talked about, it's really about accuracy and making the right decision. Whereas this video talks about how soon can you do it. It's not good enough to tell me after 5 minutes or 15 minutes that this is a human or a car. I need to know it in real time so I can actually act on it and make decisions. And this is another very interesting application of deep learning, and it's everywhere. The surveillance cameras to drones flying to self-driving cars, they all use this notion of visual conception driven by deep learning models. This is another interesting, very different example, which is generative AI. So AI can not only just predict things, it can also generate things from what it's learned. Sorry, get back to this. So what this is showing is, this is from NVIDIA, and what this shows is it's basically learned what celebrities look like by training thousands and millions, thousands of photos. If you look here on the bottom right, it's showing you how many million pictures were used by the model to learn what celebrity faces look like. And these are all fake celebrities it's making up. Basically, it's dreaming up what a celebrity should look like. And not only that, it can then generate one person from the other by interpolating between what it's learned, right? And this is an example of a generative AI. Generative AI is something that can create things based on what is learned before. When we talked about the last two videos, you're really just predicting something is, a car or some tumor or not. Is it a car or not? Whereas here you're actually generating things based on what you've learned. And this will be a very interesting aspect of, when we talk about adversarial machine learning or AI that are going to generate threats on their own in the future. This is an example of how they can learn from past examples and create variants that are similar in nature using those past examples. Okay. Are you guys able to see the videos on screen? Okay, just making sure.
Yeah, looks good.
Right. So we talked about detection, the computer vision. We talked about, this is called generative AI. It makes things. Another very interesting thing is called sort of a recurrent, like it's a reinforcement learning, where you can actually teach an AI with a reward system. So for example, people have taught AIs to be able to actually play Mario, right? So what it can do is, there's a neural network here, and it's actually learning which, on the right side, you'll see, these are the keystrokes. So should I go A, should I use A, B, X, or Y? Should I use up or down? And what it's doing is, this is called reinforcement learning. So it tries all kinds of combinations until it finds the combination that works well, right? So, and that's what the training means. In every machine learning model, you have a training phase. You learn from your mistakes, right? So here, the computer plays this game millions of times, and it finds what combination of keys actually work and what makes it die. And over time, it's able to play this game, and actually the fitness score, every time it learns, it gets better and better and better. Till in the future, it actually knows what keys to press such that it can manage to play these games, without dying. So here's an example of an AI that's already been trained, given a lot, having played millions of games to see what happens to it based on what it does. Right? So this is an example of a learning AI where it's learning from mistakes. It's not just predicting based on data. And finally, this is another interesting application which has come up. People, deep learning models can also be used to, learn things like, what kind of music is something. So this is a pretty interesting video. I want to just quickly play. So just to explain here, what's happening is the model is hearing the music and it's predicting what kind of music it is just based on the notes that it hears. So on the top right, you can see, it's predicting classical, right? Whereas on the bottom, it's like a handmade rules-based system, which is trying to do the same thing. And as you keep changing the kinds of music that you have, it's able to tell, this is Baroque versus, the hand-tuned system is not able to do that well. And similar and so on and so forth. So what this is showing is, you can always build some kind of rule-based system. So by hand coded, it means, okay, if I hear this kind of tone or pitch, then it's jazz. If I hear this, then it's classical. This is a pretty, you can find a parallel with, some rules you might write in Splunk. You have to sort of figure out a rule for doing something. And that's always hard to create a rule that will work for everything. Whereas what deep learning does is it learns from data. So given enough examples of, what jazz looks like, it's able to better predict what jazz is versus a hand-coded model that can be more brittle. And go to the last video now. This is actually some from a group that used to work with us at Qualcomm. They're from Korea. And what they do is, it's pretty interesting. They actually can translate. So they do real-time translation from one language to the other. But not only do they do that, they actually translate the voice of the speaker itself. And they mimic their intonation. So this is again done using a deep learning model. So I just want you guys, this short video.
My name is Morgan Freeman. Nayulan Morgan Freeman Imiya. I never learned Korean, but Neo Sapiens makes me to speak Korean. Nanin Hangubar Beon Chakyasamiya. Pura Neo Sapiens Dopune Hangubar Hesikiyasniya. I prepare this technology to discuss business opportunities in interactive media. Interactive media bunyai sao kive tehaya namiaki sao ikisujan biasmiya. Please commercialize this technology with many partners. Man partner
So this is an interesting example of, it's transferring the style of the speaker's voice as well as translating the language in real time, right? So this model is an AI that's been trained with many examples of, language to language, like, what words mean in English versus Korean, but also learns the intonations of the speaker and translates that into the translated language as well. And you can imagine that there are many examples. There are many, applications here. People are doing, for fake news or, deep fakes, and all kinds of things can happen with these kind of technologies. So I hope this gave you, all of these videos give you a good sense of the capabilities of, AI and ML and what it can do in terms, in all the different things that we humans do in the physical world: computer vision, speech, navigation. All of these kinds of tasks are something that the AIs can learn by looking at vast amounts of data from the past. So I want to stop you quickly and just, are there any questions that people have at a high level? What this is? So the next section is going to talk about how does all this actually work. So we talked about all these interesting things. What is it that's making that work, and how does that really happen from first principles?
Yeah, we don't have any direct questions quite yet. Myself and Brian liked that last video. It was pretty awesome. And Brian said deep fake alert, which I know you may address a little bit later, but he did just ask, and I think you might also address this later, but where do neural networks fit into this model? And
sure. I'll talk about it here. Yep. Yeah. So I think we can start with the, I'm sure you guys have heard all these terms being bandied about. There's AI, there's ML, there's deep learning. So people bandy them about in different contexts. And so in our definition, what at least I aspire or ascribe to is, any AI, artificial intelligence, is something that processes information, acquires knowledge, and makes a decision. It's a very, very general thing. I mean, you can think of even an if statement, which takes something and is input and makes a decision, can be considered some kind of an AI. It's a rule, right? At a very, very high level. Right? That's you get some information coming in. You have some knowledge. Your knowledge could be, a model. It could be a simple rule. And based on that knowledge and the information input, you make a decision. That's AI, right? So machine learning is a subset of AI. In machine learning, I learn from data, right? So data could be, the pictures of tumors. Data could be waveforms and their translations. Or it could be, language. It could be English to Korean. All of these things are the data. Based on training from that data, I make a model. And model, think of what a model is it's a piece of software. So it's like, it's a file. In the end, the model is one large, binary blob of, an object that you do a computation on. Think of it as a large matrix that you multiply numbers on, right? And then when you give a new input to that model, you can make a decision. It'll tell you tumor or not, Korean or English, or, the translation or whatever you were trying to do, right? So really what we call training is I'm taking data and I'm making a model out of it. That's what training is. And training is an intensive process that's done offline, right? So initially, when we started this company, for example, to train one model used to take us 6 months because, the GPUs were, the first generation, or depending on your compute power and the amount of data, training can take very long time, right? And so The difference between machine learning and deep learning, I would say deep learning is a subset, even more, smaller subset, where we don't have any feature engineering. And I will get into this later. Don't get flummoxed by this word. What feature engineering means is we don't tell the model what it should look for. Like, for example, I don't tell it, like if I'm trying to detect a car, I'm not going to tell it, hey, look for something that looks like a wheel, look for glass, look for a rectangular. We're not going to bias the model by telling it what we think is a car. We let it learn from the data itself, the concept of a car. And we'll talk about this more and more in the talk. That's the key difference between machine learning and deep learning. In deep learning, you don't design features. The human does not design the features. And that's the key reason, one of the big reasons why it's so powerful, because deep learning learns the best representation for the task by hand. Right? So you can do this. So if it's a speech waveform, I don't have to tell it to take the Gaussian and do, I don't have to tell it to transform it in a certain way. It'll just take the raw speech waveform and figure out what it needs to decide if it's, what is the word that's being spoken in that speech waveform. Similarly for a tumor, I'm not going to tell it to look for spots and things like that. I'm going to tell it, here's a picture, here are the pixels, you figure out what's important to look at. And that's the key difference between machine learning and deep learning. And I think we'll keep going into this difference in the talk. We really understand that small but subtle difference makes something brittle like machine learning versus something like deep learning, which you can actually use to drive a car. Okay, so for any AI, ML, or DL system, the goal is to take some data and make a product out of it, right? As an example, you have a bunch of data about English language with their translations, and you want to have a product that given somebody spoke onto your phone and you can translate what the person is saying. That's the product. So you want to take data and make a product out of it. So examples are, you have this picture and I can segment the picture, find all the humans in red, can find the car and I can separate the trees out. I can tell what these things are. That's the product. I can take someone talking, I can capture their sound, and then the product tells you that, hey, they're saying this is hello and this is world, right? Somehow it is able to figure out this is hello and this is world. Similarly, you can think of taking network traffic. If you have enough data about malicious versus benign traffic, could you be able to take that and say if it's benign or malicious? Something new coming in later on. That's just to give a context of how these, what we want to achieve with machine learning. The problem is, for us as humans, it's very easy. I mean, if you guys look at this picture, you can clearly see this is a car. It's obvious, right? Because we have learned, our brains have learned this information over, over the years that we've been growing. A good example is if any of you have used Amazon Alexa, it's actually trained with as much of speech data as a 17-year-old would hear in their lifetime, right? So when they train Alexa, they're pumping up so much speech data into it. It's almost the amount of sound that a 17-year-old would hear from the time they're a baby to the time they're 17. And that's what it takes to train it. So it's very similar to how humans learn. They need that volume of data to really be able to reason about speech. Okay, but computers think very differently than humans, right? So when a computer sees this picture, they don't know what a car is. They don't have a concept of human or anything. All they see are a bunch of pixels, right? So this is, let's say, this small tail light. It's a bunch of pixel values, RGB values of that image. That's all it's seeing. So how do you take that and figure out, this is a tail light, and on top of that, how do you figure out this is a car, right? So for the computer, it's a pretty hard job to make these kind of decisions, and that's why you need, something, a complex mathematical technique like deep learning to actually do these kinds of things. And we'll talk about how that actually happens when you train. So this is a fundamental problem, right? So if I ask any of you to say, what is a car? How do you define it? It's hard for people to define comprehensive rules. Like, how do you define a car? You could say it's a box-shaped metal thing with 4 round objects at each corner called wheels. You could, write a rule about that. Or it's a vehicle moving on wheels, or it's a road vehicle, typically with 4 wheels, powered by this. So it's very hard to write a rule that when applied to any random object will tell you correctly it's a car or not a car. So these are fundamental, the problem that we human excel at naturally are actually pretty hard for the computer to do, right? So what machine learning is trying to do is take all this data, right? And someone has to teach it. So somebody has to tell it, hey, this is a car here, this is a car, this is a car. So give millions of pictures like this, so much that the model can actually learn what represents a car. And given this training that happens offline, so let's say I took a week and trained, gave it like 10 million images. I finally have this model file, and then I take a new photo and send it to this model. It can then predict that this is a car based on my past knowledge of what cars look like. right? And this knowledge, one thing very interesting here, this knowledge is very generalized. It's not that I have to see the same kind of car again. It's learning the general concept of a car in a very soft way, just like humans do. And that's why it can generalize. If you think of like a malware, it's not that I'm learning signatures of the malware. I'm learning, here are all the different variations of how people write a thread. And so when I see a new one, I can sort of say, okay, this is much more like a thread than something that's benign. So similar kind of analogy between security and computer vision here. Similarly, if you've not, I may not have seen this specific SUV before, but I've seen enough things that look like that I know are labeled as cars, that I can predict that in some new data that's coming in. So when you have machine learning, this is the basic notion of machine learning. I've taken a bunch of data, I train it, and I get a model, right? And then the model can make predictions in the future. Now there's two kinds of machine learning, right? So there's machine learning where I have data and I have a label. For example, I have a bunch of pictures of cats and dogs, and I have a label saying this picture has a cat and this picture has a dog. And so that's the label, and you have the data. And so that's called supervised learning. So somebody's supervising the learning and telling it what it should, what those things are. There's another interesting area called unsupervised learning, where I just don't know what the data, I don't know what it is, but I'm trying to learn groupings within the data. So it could find all the cats are sort of similar to each other. They form one cluster. I don't know what the cluster is, but here are all the things that are sort of similar. And then I can go and name it a cat. And then it might find that all the dogs are similar to each other. They're not all the same, but they're very different from what the cat is. And so these kinds of models find unsupervised clusters of things. Right? And this is similar to what you will find some, I guess if you guys are doing anomaly detection in your SIM or your Splunk, those are the kinds of things. It's trying to find anomalies or clustering things together to group things into categories that make sense based on what the data is. And notice here, there's no label on the data. So nobody's telling the AI what something is. It's just raw data being fed in. And so if you look at machine learning, there's many things you can, there are many kinds of things you can do with machine learning. So one type of thing is classification, right? So it's supervised means somebody's giving me data saying this is class A or class B, this is a cat and this is a dog. And then given the new picture, I would say if it's a cat or a dog. Another example is regression, where it's supervised, but I have to make a prediction. So for example, I have a bunch of data about homes. I have the square footage and neighborhood and where the schools are, blah, blah, blah. And can I predict the home price? So given a lot of data from, let's say, Zillow or Redfin, with all these examples and the final selling price, I can then take a new house with all its information and then predict what the sale price is going to be. And that's an example of supervised predictive machine learning problem. Third problem is clustering. So I don't know what things are, but I can group them together. So I can say these data look like cat, these data look like dog, this looks like a giraffe or something like that. So it's basically separating data out into different areas. And the final kind of machine learning problem type is anomaly detection, which is completely unsupervised. This is essentially I learn what is normal. So think about your network. You go and say, okay, it's very normal for this node to talk to that node 5 times a day and send this much data, right? And so anything that goes away from that learned pattern is an anomaly, right? So notice that these kinds of things, anomaly detection can be very noisy because it's hard to know whether you really learned what normal is to find the abnormal. Whereas cases like classification, you can make a pretty good decision because you've learned the classes before, and you can say, is this a cat or a dog? Is this a malware or not malware? So the kind of problem you're trying to solve with machine learning, determines how good it's going to be at doing that. It's very hard for anything which is using anomaly detection to be very accurate because of the nature of how it's trying to solve the problem. And so these are examples of, a key thing I try to tell people about any machine learning or deep learning or AI, that it's all about the boundaries. So one key takeaway is to remember is that all machine learning or deep learning algorithms live and die based on how good their boundaries are. And here's an example of that. So if you see this data on the left side, it's basically a bunch of red and blue dots, right? So think of the red could be cat and blue could be dog, or red could be malware and blue could be benign software, right? And what machine learning tries to do is tries to find a boundary between these data types. So if you use nearest neighbors, it's saying, okay, anything in this area is going to be red, anything in this area is blue. If you use a decision tree, which is another kind of machine learning, it tries to draw boundaries using squares. If you use linear S, these are all different machine learning algorithms they all draw different boundaries between the data, right? And depending on how you draw the boundary, you might have a good, a good system or a bad system. For example, if you look here, it's not very good in this area. If you look at in the middle over here, there are lots of blues where it's going to say it's red. These are all the mistakes that the machine learning is going to make, right? So depending on how fancy you can draw if you can draw your boundary in a very fancy way, nicely separating all the red and blue out from each other, then you're going to make a good decision. You'll have low false positives and you'll not miss too many things. And so this is a key thing to understand as to why does, deep learning or machine, which one is better? It's all about how good is the decision boundary, how complex of a boundary can I draw between the A and B data or the good and bad data to be able to make the right decision in the future. Any questions on this one? Because this is a pretty key aspect to understand before you go to go further here.
None yet. If some pop in, I'll let you know. But
sure.
As of right now, we have no questions.
Sounds good. Okay, so that's one thing to remember. It's all about the boundary. So having seen what machine learning is, so just to go back, we're trying to take data and learn from it. So what's the difference between machine learning and deep learning? We talked about this notion of there's no feature engineering, right? So in machine learning, you have a human who's going to decide what to look at, and then the machine will just figure out rules on top of the stuff the human told it to do. So for example, I could tell it to look for circles and spheres and rectangles for cars, and then this guy will say, okay, how many rectangles are there, and based on that we'll decide whether there's a car or not. So in machine learning, the human is sort of biasing what the the AI can look at. In deep learning, the model training automatically learns the best representation of the data. So it will just take the raw pixels. It's not going to ask you to tell it what a car is. It's going to look at the raw pixels and try to understand in multiple layers what this entity actually is. Right? And this is very similar to how the brain works. And we'll talk about why this is similar to how the brain learns and why this is less brittle. So it's much better at not making too many mistakes when you learn this way, versus when you let a human decide what to look for, you're biasing that with the human knowledge. And that human knowledge may not be perfect. You might have a few ideas of what you think a car is, but it may not be a very general description. Or you may not have seen all the cars in the world, or you may not know how to encode that into a rule. Whereas in deep learning, you don't have to encode any rules. It learns from the raw pixel data itself. Right? So no feature engineering is a key difference between deep learning and machine learning. And so deep learning is also synonymous with neural networks. So what deep learning does, it basically has many layers. So the input could be, this is the input layer, which is basically the raw data. It could be the pixels from a picture. It could be your speech waveform. It could be all the binary objects inside a malware. It could be all the header fields in an HTTP GET response. So the input could be anything, but it takes these inputs and it tries to encode them in different ways to come up with some output in the output layer. That's what deep learning does. Deep learning essentially involves training neural networks. Right? And this is not something that's just happened now. It's just something that is useful now. So the history of deep learning is that it was always called a neural network, and research on how neurons might work actually started in the 1940s. The first application of this to some small toy real-world problems, were in the 60s, and there was some multi-layer neural networks first proposed in the 80s as well. And training a neural network by backpropagation, which is what is used in deep learning now, was first proposed in the 1970s and rediscovered in the 80s. What is interesting here is that because the computer that people were using then were so they just couldn't do this much work. So what you could do with neural networks was really limited. Right? Because you could imagine you had like 10 nodes in your neural network. So if you have this kind of a picture, you probably have like this smaller neural network instead of like millions of them. And then you keep training that, it would take hours and hours and hours, and you could do something very small. Right? That was one of the issues with neural networks. And then what happened in 2012? 2012 is when we had a turning point in training neural networks. So researchers in Stanford and a few other places, University of Toronto, and Google itself, they discovered a way to use GPUs to train neural networks. GPUs were getting advanced, just for playing all the Call of Duty and those kinds of things. And people figured out how to use those same instructions to train a neural network much faster than using a CPU. So you could train much bigger networks. Bigger networks can learn better things and make fewer mistakes. You could learn on larger data sets. That means I could take terabytes of data instead of megabytes and gigabytes. So I could, make a more interesting model, and I could do it in a reasonable amount of time. And if you had a model that takes you 2 years to make, and then you figure out it doesn't work well, you just can't experiment with it, right? So what GPUs allowed was experimentation. So researchers could try, well, let me try this parameter, let me try this architecture. Because in a neural network, remember, you can play around with all of this stuff. You can decide how many of these layers are there, how many nodes are there, what's the function between these, what's the weights. So there's almost like a million parameters you could choose here. And if you have enough compute, you can let the computer experiment with all those parameters. So it might try like a billion trillion different combinations of things to figure out what works the best. So if you look at this graph over here, what it's showing is the ImageNet classification error. ImageNet is a standard data set for computer vision of photos and their classification. Like this is a mug, or this is a car, and it tells you what's the error. So in 2011, you had like 26% error, mistakes happening in the computer vision when you were actually looking at these images. And over time, these numbers have gone down to 3%, and now it's much, much lower, right? So imagine that this is like your false positive rate. So if you had an AI that could, make mistakes a quarter of the time, you can't really trust it and use it for anything useful. But what's happening with deep learning and the fact that you can train it with lots of data and lots of parameters, is you can drive this mistake percentage down to very, very minuscule numbers, below point, can get to 0.1% and lower. At which point it becomes useful. So that means you won't misclassify tumors. You won't say it's a malware when it's not a malware. So at that point, it becomes something a domain expert can actually use and trust over time to give the right output, right? So,
Hey, Saumitra, I don't know if this will be answered later or not, but I'm gonna toss this question to you. Someone said, "I hear that neural networks is mostly matrices. Is this true? If so, how does that work?"
sure. Ali, you want to take that one? I think you'll have a good answer.
So, the short answer is that yes, we use a lot of matrices in calculating, the parameters that we need both for training and evaluation, deep learning model. As Saumitra is bringing up this picture, if you look at this X1, X2, X3, S4, X4, all these layers that you can look, all of these things are actually shown in numerical format in most of the times. And if you put them in a vector representation, and then those vectors, when you have multiple layers, actually forms into a matrix format, you can make your calculation very efficient, very effective. Okay, so when you're moving forward to calculate all your weights, and when you're moving backward, which we call it basically back propagation, in order to optimize the model that you have and calculating these weights, that vector and matrix representation makes it much easier for you to efficiently calculate these things. And that's the key here. And it's not only related to deep learning. As Saumitra mentioned, both of us are coming from communication background as well. And right now, the cell phones and the mobile communication and your laptops, when you're calculating the performance of the communication, these have multiple antennas in them, and all of those calculation also is done into matrix format. So using matrices makes it much more efficient from calculation perspective. So the short answer is yes, but it's not limited to deep learning. Any kind of vector analysis that you do, you end up using matrices. And GPUs are actually, that's a very interesting point, is that GPUs are very good on doing of those vector and matrix calculation. And that's the key thing. That's what happened in 2012. We learned an efficient way of using this matrix representation to use with these GPU tools that are very good for signal processing and numerical calculation to train these models. So all of these things are combined together.
Yep. And one thing very interesting, and one interesting, we were at Qualcomm, so we were looking at low power. How do you compute? So one of the big efforts that my team did, in fact, actually we had somebody from UT Austin who actually worked on that, was looking at basically, the basic linear algebra packages. So all these software libraries that do, matrix multiplication and those kinds of things. How can you make them really, really fast by using the CPUs in interesting ways, by looking at the cache, by looking at how often you hit memory, by, so those kinds of optimizations were done. In fact, by even having instructions directly in the CPU that directly do matrix vector multiply, instead of, calling a loop on, you could write a matrix multiplication by having for loops, or you could directly call one instruction which does it in memory directly, right? So those are the kind of things, both GPUs and CPUs have been, like Intel has been crazily trying to catch up with NVIDIA on trying to do better matrix multiplications on its CPU, so that they can take away. They also lost a lot of money to the GPU guys because of deep learning, right? Because all these companies started buying tons of GPUs, and that's why the best class, at Blue Hexagon when we started, we had to invest in a few machines, and each of these machines are like 50K, and they have like 16 GPUs in them, right? Because GPUs are so expensive. And the other problem was GPUs started getting used for Bitcoin mining at the same time. So there was this whole very interesting, supply problem where all the Bitcoiners and all the deep learning people and all the gamers were fighting for the same GPUs. And so the cost, so NVIDIA made a lot of money in those, in this whole decade because of that.
Excellent. There's actually another question and then a statement. If you want to take that now, or you can wait, it's up to you.
Sure, I can take it now.
It says, let's say that the neural network arrives at some solution. How do you know the supporting way that the solution was achieved?
Ali, you want to take that, or should we wait for another slide for that one?
I think your evaluation slide and the one that you're talking about, the overfitting and underfitting, would be.
Okay, yeah, we'll take that later in 6 slides from now.
Cool. And then the other comment that could be relevant, you were talking about, all your GPUs. It was more of a comment than a question, but storing billions of possible ways / paths would seem to be very hardware dependent. And I know we've, Saumitra, we talked about that on size and storing models and things of that nature when we talked previously. So I figured that'd be a good comment you may expand on if you liked.
Sure. Yeah. So I think there's two parts to deep learning. One is the training, right? So in training, it's all offline. It's not running, it's not making prediction. It's just training. So there, typically people like we use AWS, we use GCP, or we have our own colo, where we train these models with our own machines. We actually built our own machines because it's much cheaper than, using the same machine on Amazon, for example. But in that case, you're really, using a farm of GPUs, and the whole trade-off is how long till I get an answer? I want to make a model and then see how good it works, right? If it takes me 3 weeks to make the model, then I can't iterate quickly. So you want to quickly train a model in 3 days. You have some idea, okay, I should use these parameters, I should use this data, let me see how good it does on new data. And then I want to try different experiments. So you want to use a lot of GPUs when you train. Once you have a model, then you want to run it live, right? You're running it on a phone to detect your speech. You're running it inside a car. So if you look at Tesla, these guys actually run like a Dell. It's like a 1U server. Like if you've seen any of your Dell rack servers, they take a 1U server, they dump a GPU into it, and then they just run the software there. So that's actually called inference. So in inference, I may not need to use thousands of GPUs. I'm just giving input to the model and getting a prediction out of it. And that's a different kind of computation. So companies now, they're actually making inference chips, or even an Intel is actually using special instructions in their Xeon CPUs to make the inference faster. In fact, we use some of those kinds of things as well in our platform, so that you can quickly make inferences, as you get data coming in. You don't take too long. So that's an interesting area of, training versus inference. They require it's a different computation that you're doing when you're training, because as you said correctly, you're trying out different parameters and you're going back and, you're trying to converge to a solution. Whereas when you're inferencing or when you're making predictions, all you're doing is, doing matrix multiplication very quickly. I'm getting an input and I'm giving an output. And the way to make that faster is different from the way you make training faster. And there's actually entire companies that are focusing on that. In fact, one of the sister companies, we are funded by Benchmark Capital. Another company that Benchmark funded is called Cerebras Systems. And they make a supercomputer for training, which is now being used for finding a COVID vaccine at LBN, Lawrence Berkeley National Lab. They bought one of their chips, and it's solely focused on training. It can train as much as thousands of GPUs, right? And so the training problem and the prediction problem are sort of different. And you're finding that chip companies and server companies are focusing on making hardware that optimizes for one or the other use case.
That's good. I was actually going to ask that. You kind of led into it. It's like a Bitcoin mining, right? They started making ant miners that were very purpose-built hardware just for doing coin mining, right? As opposed to just using GPUs. I was curious if they're starting to do that same thing with hardware for, machine learning and deep learning.
Yes, and it's becoming very specialized. So, things like GoPro, I think, you might want something done right on the edge. You have a camera somewhere, you might want to figure out, oh, if I see people only, then I send something to the cloud. So I may want to do some basic inference there to at least understand what's happening and not keep streaming all the data back to the cloud. It's very expensive. So you have also this notion of edge inference, or on the edge, I want to make a decision. And then when I send it to the cloud, I can make a better decision with lots more data, or lots more time. So yeah, you're right. I mean, one of the interesting things that Google has done, they actually have a It's a TensorFlow chip. It's a chip used to actually do inference. And some of the talks that their folks gave was if they hadn't made that chip, it would bankrupt them just to run all the inference that people are talking on their phones and looking at Google Photos. All of that stuff, if they had sent it to the CPUs, the data center bills would have been astronomical. So they actually had to have custom hardware to actually do those deep learning inference so that they could keep the costs down, both in terms of electricity and in terms of time it takes. So they could actually have these billions of people, asking questions all the time to their, deep learning algorithms. So
Yeah,
that
and
was
on the
interesting.
flip side, and kind of related to security side on malware and detection, because that's where you're kind of at. I think it can be used for other things too, but the idea of the difference in machine learning and deep learning we talked about as far as storing that model on the client side, right? So it can make decisions right then without having to be connected to the internet. Difference seems you can from what you've discussed with me previously, you can kind of have a bigger, faster, smarter detection engine with deep learning than you can with machine learning on the endpoint, for instance, for detecting malware. So I'm sure you might get into that, but that was another
we'll get
cool
into
thought.
that. Yeah, but that's so size, the size of the model and the complexity of the model does matter. So if it's on the endpoint, you might have to choose, how big you can make it versus, a signature database. But it does very well. If you could do it in the network, you can probably do it even better, larger model, which is less mistakes. Then you go to the cloud, but the problem is, now you have to send everything to the cloud to do inference over there. So that's why this, edge concept and how much resources you give machine learning determines how good an output you get. If you just have like a wimpy laptop, you can't expect it to do, really amazing things with machine learning as well. We'll get into that a little bit. So I just want to talk about, a lot of people bring up this brain versus deep learning. It's a brain. You have Google Brain. And so some of it is, I would say it's more inspired than mimics the brain. The brain is infinitely more complex than deep learning. I would really say the brain is what inspired people to think like that. So this is an interesting picture here. If you can see, it actually shows the different parts of the brain that do different things. So I think the LGN is used for auditory, information. The retina, information comes here. Some of the parts of the brain combine information you're feeling from your hands, right, as well as what you're seeing and what you're smelling, right? So what is interesting about the brain is it's not that it doesn't treat computer vision and speech and all these things it doesn't treat them as different models and different ways of doing things, right? It has one uber model. It has one neural network which is way more complex than what we have right now. The biggest neural networks we have are similar probably to a mouse, right? That's in terms of number of neurons and all that. I mean, they're getting bigger and bigger over time. But the brain has infinitely more neurons, and also in the brain, what happens is the timing of the signals matter. In deep learning, the timing of the how one neuron talks to the other doesn't matter. Just the fact that one neuron sent a weight to another neuron. So it's much more simplified. It's a much more simplified notion of what a brain does. But what is interesting to know is that it's very similar in terms of inspiration and and thought process, because the brain doesn't learn in one layer. It's not like you get a picture in your eye and right away it's a car. There'll be some part of the brain that is good at doing shapes. So it'll look at like edges and lines and circles. Another part of the brain will put that together into maybe a structure or a human shape. Another part might say, oh, this is a face, and then it knows it's a face. And all of these parts of the brain have different delays and how many milliseconds it takes you to recognize certain things, right? And so what is interesting is deep learning also has a similar concept that there's multiple layers and each layer is learning something different. And then at the end, you're putting all the knowledge together to make a better decision. So you're not making a decision based on, just pixels. The pixels become lines and shapes, and then the shapes are put together into, larger concepts like a face or a body or a car or a tree. And then you can you can have better reasoning about what you're actually looking at right now. And we'll get into, I know this is hard to grasp right away, but we'll get into how the neural network sort of mimics what a neuron actually does, right? And this is an example here. This is showing an axon and dendrites and how impulses happen in the brain. Similarly, what happens in neural network, this is considered a neuron in a neural network on the right side here. And what this guy is doing is taking input from the nodes behind it and computing a mathematical function. So it takes all the weights and computes a function. And then there's an activation function as to, when should I activate the output of my neuron to go somewhere else, right? So, and all that training does is adjust these weights essentially. So I have some input, I know what the output should be, and let me adjust all these weights. I try all kinds of iteration. Let me make this 0.1 point. So you adjust all these weights and train this network such that you have the best performance on your training data. Right? And that's really how deep learning runs. At a very basic level, you can think of as I'm trying to adjust all these weights and connections, and maybe I can play with these functions such that given some input and my known output that I have the lowest error between my input and output. Right? And then I can take that knowledge that I learned and apply it to a new input for which I don't know what the output should be. Then I'm making a prediction. Adi, you want to add anything here?
No, that's it. So basically what we are doing, just one point that I want to bring up is that the objection, as that question that we discussed, the objection is not, the object is not, target is not always to make it the best on the training data that we have. We wanted to actually have the generalization as well. So it works the best on things that it sees and things that it will see later. So the generalization is also one of the things. So the training process consider both the data that we have at hand and the data that we may not see at the time of training in order to make sure that the model generalizes better.
And this is very key. For example, if you look at, I'm sure many of you guys use VirusTotal or some of these threat services. Every day you'll see probably 300,000 to 1 million new samples or IPs, domains, or new PCAPs or whatever you want to call it. And the model shouldn't just do well on the past 10 years of what it trained on, because it's already seen them. You can obviously find a way to fit the pattern. It needs to do well on the next 6 months of data, which is not seen, right? So how do you make a model that doesn't so it's important in machine learning to not overfit your data to the past, but also look at how you're doing. If you take a random sample out from your data and tell the model, say, tell me, the answers for this, it should do well on a test that has not seen the answers to before, right? So you can fit your model to your data, but you have to make sure that it does well for the future data, which is what it's really going to do. Like if you learned all the trees you want, but when you put it in the car, it's not going to see the same tree that it learned. It's going to see a brand new tree which it's never seen before. So it's very important to train machine learning to do well on the data that's not seen, and make sure your model is not being trained in a way that biases too much to the data that it's already seen. And that's why training machine learning is it's not something you need to try it out and have some experience with it. And some of this is intuition. Just like you guys, you can intuitively tell when you look at your network logs, or you can say, oh, this looks funny to me, because you got used to what so it's one of those intuitive kind of things that machine learning scientists understand as they play with our different parameters in a model, how the model is working and what's working well and not well. So that's really the art behind, you can't just take open source code and run something and get an output. You really have to spend time understanding. I think someone asked that question, how do you know what it learned and why it learned it? Those are all important questions you can introspect. So we call this model introspection, how to understand why it's arriving at a decision. Hopefully it's not learned some weird thing, which is more of a anomaly than a real thing. And as an example, if you give a model or a bunch of packed samples, it could just learn the packer and say, oh, this packer means it's bad. Whereas you might have some benign software that also uses that same packer. So you have to be careful not to bias a model to over focus on one thing and use that to find the right answer. So those are the kinds of tricks you have to play as a person who's making a machine learning model to make sure that it's working in the general sense. Right? So the question here is, yeah.
Before we go, I want to bring up one more point, is that for everybody, especially even if we don't have that much experience with deep learning or training, that intuition, usually the way that as human we treat things normally, and we observe things and we make a decision, is actually a good intuition for us to understand how the deep learning works. For example, there was some discussion that you brought that was discussed here, that how big is this information and how do you fit this information into a model? When we learn about the tree, we don't remember all the trees that we have seen in our life. We've seen them and we learn the tree, and we have that knowledge of what is a tree, but we don't remember all the trees that we have seen in our life. And that's exactly what happens here. When the model sees all those different images and it's terabytes of data and millions of the samples that it sees, it doesn't copy them, it doesn't save them all. It saves what it learns from them and adjusts its structure in order to have the capability to make a decision based on what it's seen. So us as humans also behave the same way. If we see a car, we don't remember all the cars that we have seen in our life, but based on the things that we have seen, we know how to determine that that object is a car. So usually when you want to understand how deep learning works, it's very good to be conscious, aware, and see how your brain works on observing things and making a decision. And it's actually really helpful. It gives you a very good intuition.
Yeah, it's a really good way to define it for sure. That helped to understand it even more.
Yeah. And that's actually very interesting. If you look at let's say, this is actually a good correlate to signature-based and ML systems in security. Like if you have a firewall, remembering everything would mean I have to know the MD5 or SHA-256 of every single thing that was ever created in the world, right? So I can go back in time, and there'll be probably billions of these things, right? And so I can't remember all of them and look at every packet and match against, hey, is this one of the 10 billion things that I've seen in the past? Because then you can't process things at 10 gig anymore, right? So there's an inherent limitation to keeping memory of things, because the number of things you keep in memory is infinite. It could become amazingly large, and it's too slow to go and look it up in a table to process them, right? So one interesting aspect I could talk to people, just calculating SHAs and hashes of things coming over the wire is more expensive sometimes than actually just running the raw features through a machine learning model. So as something deployed on a perimeter or something, it can actually scale better because it's not sitting and remembering and trying to match against a huge table. If any of you guys have used things like Suricata and others, remember, as you put more and more rules, it needs to do regex on all of them, right? And then the more regex you need to do, the slower it becomes, or the more packets is going to drop. It's something sort of similar, right? I can't remember everything in the world, I need to sort of learn some knowledge. I can't just be something that checks against a list. And that's the difference between deep learning and a signature-based system or a rule-based system, if that makes sense. And so one of the questions we ask, okay, we did all this fancy stuff. So what does it mean? How does it actually help? So this is interesting. This is from the Microsoft. They've been working a long time on speech recognition and things like that. And in 1990s, the error rate used to be like most of the time we're going to make mistakes, right? By 2000, this is the time when I was in grad school. We could do something interesting, reasonable things, but it made so many mistakes. You can't actually dictate to it. You can't like dictate a letter and it's going to get it mostly right. And it stayed like that for a long time. So in this span of time, there's probably like 200 PhD theses written at most of the universities here, and all of them are trying to improve it by 0.1% or something. So it'll go from 13 whatever percent to 15. So it was like a plateau and nothing happened. And in this 2012 timeframe, when deep learning started being used, we saw a crazy amount of drops. So this technology came and threw away like probably 100 people's life work PhD thesis, because it could improve upon all the things they had handcrafted by automatically learning the features, right? And now these numbers are going, if you go to Alexa and the Facebook face recognition, these are better than human performance at this point, even for translation. And that's what has been very interesting, that when this 2012 happened and we had all this large data and GPUs, these systems actually made something fundamentally better than what was possible before, because there's this huge plateau. This is the age of machine learning, and then you plateaued it at like maybe 20% error rate. You can't deploy something that makes 20% errors in practice. You can use it for toy examples, you can have fun with it, but you can't deploy it autonomously or even semi-autonomously. And that's what deep learning gives you. It gives you enough low errors that you can actually use it in practice. And remember that when we talk about errors, even 1% is a lot. Imagine a typical network has 10 gigs, there's thousands of transactions. 1% error is also very large. You're going to have all kinds of false positives. So it's very important to get these numbers as low as they can be to make the system usable. Similarly, for the the tumor example, if it keeps saying this is a tumor, that's a tumor, the pathologist is going to give up and say, I can't use this because it keeps taking me down this direction. I don't have time to investigate all the false alerts, right? So keeping this low is actually very crucial to making it usable. And that's why deep learning has made some of these things usable. That's why we couldn't have these Teslas, these things happen, in the last decade, and we can have them now. This is another example. What used to happen before, we talked about computer, machine learning, basic or handcrafted models. If you tell it to look for a mug, it's going to say this, right? It's going, oh, this looks like a mug, it has a circle. Oh, this also looks like a mug because it looks like the body of a mug. Even this coffee thing looks like a mug because it's a small mug, right? And this has a handle, so it's a mug as well. So when you have handcrafted features, these are the kind of mistakes you make, and you might actually miss the real mug. Whereas when you have deep learning, you can actually get this very clean distinction without all the false alerts on the other side, right? And that's the difference that deep learning has made from machine learning. It's able to do these things better because we didn't bias it by telling it what to look for. We didn't tell it to look for this, look for this curved handle and look for this circle. We let it learn generally from the pixel itself. And remember, we talked about no feature engineering. This is what you get when you don't have feature engineering, right? And that's the key thing to deep learning. Right?
To bring it back, just for everybody to be again have an intuition. When as human you look at this mug, you never you just know it's marked. Okay, so you don't make the determination. Hey, it has a handle and it has a round and it has a circle thing and I can put liquid in it, so it's a mark. You never do that. You just look at it and know it's raw. It's a mark because your brain, your eyes actually collect all those raw information from the object and process it and make a decision. So it is important. That's the difference between the feature engineering and using the raw data. Your brain already does that. So if you look at any object, whether you have seen it or not, you instantly know what it is. And then when you're being asked why it is, then you start to rationalize that. Hey, it has a handle. I can put coffee in it. I know. Look at the circular shape. So that's exactly what happens between the feature engineering and the raw feature calculation that the deep learning can do. So it's actually a very good way for you to understand the leap forward that Saumitra was showing on the previous slide. What happens at this leap forward happened? The leap forward is between you trying to make a logic on everything that you want to make a decision, rather than intuitively your brain can make a decision, which is almost always right.
Right, and this is kind of answering the does it work, but I guess you'll get into the how soon.
Mm-hmm.
Because I think that was very cool to see the the different layers of learning
Yeah.
of how it gets to that. It was very very enlightening.
Exactly. Yeah. Yeah. That's the next slide. So quick to summarize between traditional and deep learning. The main thing to remember is it thrives on big data. So if you keep giving data to traditional machine learning algorithms, at some point they hit a plateau. They can't learn. They can't be more accurate. They can't make use of it. But if you give deep learning more and more data, it's able to actually make use of that data and become more and more accurate. This knowledge gap between traditional ML and DL is the key thing that's driving all these benefits. It's able to use the data to learn new things, right? So the error goes down. And the other important point is the models can represent complex nonlinear functions. So we talked about it's all about the boundaries. How good of a boundary can you draw? So when you look at this data, let's say this is malware and not malware, or it's cat and dog, or whatever it is, it's just two kinds of data. Deep learning can draw this very complex boundary. You see these very, very complex functions. To describe this function, it's going to be, it's not linear. It's very, very complex function in multiple dimensions, but it can separate the data very cleanly into the two classes. And this means it makes fewer mistakes, right? And that's the key reason why these two things are different from each other, because they can use data and they can create better boundaries, right? And they can harness computational power to find these functions. In the end, all deep learning is doing is finding a function that separates A and B. And this function can be arbitrarily complex in deep learning, whereas in machine learning, it's, if you remember the previous slide I showed, it has to be some kind of a square or a straight line. So you can't divide data with those kinds of simple boundary easily without making mistakes. And to give an example, this is what Google Brain looks like. This is the model. This is the machine that is actually doing the training. There's a whole server room. Each of these will have hundreds of tensor units in them. So these are the kind of things that are used to train these kinds of deep learning models. So Ali, I'll let you show. So you talked about this learning in different layers, and these two slides will really tell you how the machine is actually learning in its different layers. Maybe Ali, you want to take this quickly?
Sure. So basically, what we talk about is in machine learning, we are always looking for a function. We want a function that does this, the decision-making process that we are looking. That decision-making can be just as simple as, hey, this is a malware or not, okay? Or this is a malware or benign, or it can actually play a partial game, or it actually can recognize human voices, do all kind of, or drive a car. So that function is something that we are looking for, okay? And we are talking about two things here: how to represent that function, and also how to find the proper parameters for that function. And on the right side, what you see is that this process, this training process now in more details, okay? So what happens is that we start with our training data, okay? And then based on the initial function that we have, we evaluate the goodness of the function. Okay, so now going back to the question that has been asked, how do you know that this thing is ready? Especially when you are doing the supervised learning, you know the answer to the training data. You exactly know the model should actually respond in this format, okay? And that's the way that we are defining this metric to see whether we have made a correct decision and make a proper decision at this stage or not. So of course we are going to make some mistakes, and of course we're going to get some of them correctly. The key here is that how to adjust the parameters in order to move forward towards a better function. And that's exactly the loop that we see here, okay? So we calculate the goodness of the function, okay? We find the best function, and we keep repeating this process over and over and over on the data that we have, but make sure that the function that we get in the next step is going to be better than the previous function. This incremental property, this incremental capability is what makes the training especially
Converge.
That means that we are getting to the point that our model getting better and better and better for the task at hand, okay? Saumitra, can you go to the next slide? Yes, so this is the architecture. So Saumitra mentioned that this thing is designed to learn a complex decision boundaries. And as I mentioned, this decision boundary is a function. What deep learning and neural network has done is that to give us a blueprint on how you can represent that function, okay? As you can see, we have layers, as you can see, layer 1, layer 2, all the way to layer, to whatever number of layers that we have. And each layer we have neurons, okay? So those circles, those dots that you can see, these are the neurons. These neurons actually, the system that gives us the ability to be nonlinear. So each one of these neurons, what they do is that they make a nonlinear function on the input and generate an output. This is what is being represented on the lower picture, Saumitra, that calculation exactly. So that's exactly the nonlinear function. So we get all the inputs, okay, based on the weights that are being calculated. We calculate a nonlinear function from those inputs, and we send something out to the next layer, okay? The same thing happens every layer with the input that we have, and we move forward. So this is the process of calculating the output of the model, okay? And that's basically the feed-forward process that we go, okay? So how do we get better and better? Okay, look at the picture on the very right, okay? So the objective is to get to the center of this environment when that has the lowest possible error. So these circles that you see, the level of error is the same on all the boundaries of that circle. And the objective is to move forward toward the center of that circle where the error, the mistake that we make is minimum, okay? But how are we gonna move one step at a time towards the target? What you see on the bottom, this is the process called gradient descent, okay? So what we do is that at each step, we go all the way, we calculate the number of mistakes that we have made and the number of correct decisions that we made. And based on some mathematical calculation, we found how much adjustment we need on each of the weights that connecting these layers together, okay? So that's the process. You go all the way, you calculate the prediction that you have, you compare it with the ground truth that you have, you see how far away from that. And based on that calculation, you make the adjustment that are needed for all the weights going backward and adjust the whole system, okay? So
basically all these W's will be changed. Yeah.
Exactly, these W's, all of these W's would be changed. And these W's all are being used in the calculation of the neuron, as you can see in that formula indicated. So this process, if you look at the picture on the right again, every time that you do this process, you move from one of these steps to the next one, okay? And depending on how you choose to calculate that error and how you adjust your weights, you may choose different kind of path, okay? The blue one, as you can see, is much more directly getting to the optimal
to where you want to be.
Exactly. Mm-hmm. The other one, the purple one, has much more randomness, okay? And as I mentioned, in deep learning and in training deep learning, sometimes the things that are better are counterintuitive, okay? Everybody thinks, okay, the blue one is perfect. It gets from point A, gets me to where I want as fast as possible. Perfect, it's good. But not always things are as beautiful and as well-defined as this is. They are not always convex, okay? You may have local minima. You may have areas that are minimum among the surrounding area, but not the best answer. So what you want is some kind of randomness, okay? So you see the purple image over there. It explores a much wider area. It explores a much better set of weights that it can calculate, okay? But at the same time, it takes much more time and resources for you to converge, okay? And then there are other mechanisms like the green one that has a good, a good of both worlds. It gets there as fast as, not as fast as the blue one, but faster than the purple one, and it does some search around. to give you the best idea. So basically what happens is that, calculating these numbers is just a matter of some matrix calculation, okay? And computer can help you to do that. What is important is the art of understanding what are the best parameters and how you actually move in your error space in order to get to the optimum point as fast as possible and as accurate as possible. Saumitra, we can move to the next one.
I had a statement / question that might be good. And I was going to ask something similar to this earlier. Is what are the good use cases in security or otherwise where machine learning may work better for something versus deep learning? And so the statement was right. So this type of thing works for things like identifying cars or trees or people, but there's no way that this type of system can determine a beautiful car or a handsome or pretty person. So this type of approach does not work on all problems. There has to be has to be a known good answer.
Well, we have a slide exactly for that, but just to give you a perspective. Yes, you're right. Not all the problems are designed or fit to be solved with deep learning. Okay, otherwise we would have been done. Every problem would have been solved, and there would be no gray or unknown area. So yes, there are requirements that needs to be satisfied in order for us to use this tool. Okay, but once we found a problem like that, whether it's an image, a speech, or in some areas of the security, okay, then what we have here, it wants to show there are lots of knobs that you have to adjust and you have to turn in order to get it right. So if you go one back, I just want to remove this. Yes, exactly. So remember we talked about how fast you can get to the optimum point. Okay, if your error space is not as clear as you want, you are running the risk of bouncing out of that local minimum and getting out. If you look at the picture on the right, yes, this way you are adjusting your weights too fast. Okay, that means that
this is the point where you have the lowest error, both in false positive. You make the fewest mistakes. Yeah.
But you start from the yellow point, but because you are moving too fast, you are missing the local one. You're actually getting to the place when your weights are getting adjusted, but in a wrong way because the system is now confused. And basically you are bouncing out of the local or minimum target that you have. And you are gonna wander around for much longer time. And there is no guarantee that you can come back where you are, okay? While on the other one, on the one that is on the very left, okay, you are so conservative that you are moving very slow and it takes forever for your model to find the proper thing. And it's really painful. It's really, for anybody who has done this, you have to keep looking at your monitors for days and seeing, okay, whether it's getting better and better. And it does get better, but then you don't know how long would that take. And then there is just right amount of time. So what I'm trying to say is that there are lots of knobs and decisions that you have to make in order to have the model perfect. And that's where the expertise of the data science and machine learning experts comes into play in order to be able to actually train the model.
So I think this is one important point that he was trying to Sheldon was talking about, that neural networks learn in multiple layers. So in the first layer, it'll learn simple things like shapes. Let's think of it, if this is a malware or a PCAP, it might learn very simple things like, okay, what are the APIs that are being called or blah, blah, blah. Whereas in the second layer, it might learn more complex things by putting these things together. So it could say, oh, this API was called, but also there is this packer here and this. So it's composing things together. And the third layer, it's composing them even more. So now instead of just seeing eyes and eyebrows and nose, it's actually seeing this as a face, right? Because it's taking in each of the layers is sending input to the next one. So it's sort of a hierarchy of learning. And so that's the main difference, main reason why you need multiple layers and why you actually need a neural net, because each layer learns from the one previous to it. And that notion of hierarchical learning is what has helped our brain to be such an amazing organ and doing these kinds of things. Whereas if you had a single layer or shallow machine learning, you'll be stuck with making decisions with something like this. It's hard to get to a better understanding of all the different ways things are put together to make a face, for example.
Yeah, a couple more comments. I have some other stuff to bring up maybe later, but someone said, yeah, but flip that face upside down and it's all at a loss. Is that true? What would you say about, flipping the face upside down? Are they going to be able to still notice that that's a person? It's just upside down.
That's the beauty of deep learning. That's the ability of generalization. That's the ability of not being stuck on just one kind of information. For example, when you make it upside down, you are changing one dimension, yes, but these deep learning models are working in hundreds of thousands of dimensions, okay? And that's where the system works. If you look at the formula on the very top, that's the matrix calculation happening on all the possible dimension that we have from different features. Yes, you turn it upside down, you change one dimension over there. Basically, you are not even changing it. You are adding a negative to some of those parameters. Okay, when the model can very simply detect that and realize that, hey, these are the same thing, and I have to be invariant from this kind of changes.
But that's a very good point. That traditional machine learning would be much more brittle. Rule-based systems, they'll be much more brittle to that unless the human has told him, hey, sometimes the attacker can make it upside down. And that's a very good insight, that to be invariant to some of these kinds of mutations that attackers can do or can happen naturally. I mean, you could have somebody doing yoga or something upside down. You need something that's not very rigid about how it learns. So actually, that's a pretty good example of things that deep learning will do better than at least traditional machine learning or rule-based systems. Doesn't mean you can't fool it, but it will do better than those kinds.
Oh, we'll get there. Yes, you can fool it, but
I was going to ask that, but I wanted to let you guys kind of finish your content. I don't want to make it go too long.
Yeah. Right. Yeah, I think let's get through. So the question is, as a question you asked, like, when is it overkill, right? You don't need, if you're doing a simple thing of, I'm taking like, the square footage and the zip code and I'm predicting the home price, I don't need to do deep learning. It's very simple, too simple, right? So you need deep learning when you have complex decision boundaries, where it's not obvious. So things like malware, it's not obvious what is good and bad. There's so much gray zone. There's so many things that are somewhat bad. There's hack tools. So it's a complex problem. It's not obvious, what something is. Like computer vision, right? You have a lemon, it sort of looks like an orange also. It's not obvious all the time what, you have a blackberry and you have, grapes. So these are not always obvious things. Similar, in speech processing, when you're talking about, when you're saying something, these are not simple problems. So when you have complex problems like this, and you have large training sets. So one of the reasons we couldn't do this before, we didn't have large repositories of data nicely labeled, and we couldn't run through them quickly. We couldn't train things in the past quickly enough to even have something useful. So really, when to apply deep learning is when you have all these properties. When you're very simple, so one way I like to talk about this is, if you have, let's take Suricata rules. I don't know if you guys you probably are familiar with those. But sometimes there's a very specific rule on a specific malform packet, right? That only happened once. It may not ever happen again. It's a specific CVE. And there's nothing general to learn from that. So it's not something that you would take deep learning and apply to, because this is just one example and there's no counter example, right? So there you will find, and in fact, you'll find there's very few rules, very specific rules you'll find it's not in Suricata for handling those kinds of things. But if you look at 84% of the rules, every day there's hundreds of rules coming out. They're basically trying to see, okay, here's a different kind of C2, here's a different kind of malware, because all the bytes are changing all the time. So that kind of change is something that can be learned by deep learning. So it's not that you can solve everything. You can solve the important parts of the problem that are very large in scope, which are changing a lot, which are a lot of dynamics in them, where it's hard to express them with thousands and thousands of rules every day, right? And that's the key. Instead of writing hundreds of Yara rules, you're basically having a model learn the patterns on its own. That's the kind of thing. Whereas if it's a very specific, here's an SMB version 2, eternal blue attack, it's a very specific crafted packet. It's not possible to learn that one specific. Then it's just a rule that you're applying there. And that's why it's important to know when you can apply deep learning to a problem and when you shouldn't.
And just for the example that you mentioned about the beautiful car, whether it can recognize whether a car is beautiful or not. If we can define that, and if we have enough labeled data that says, hey, these cars are beautiful, these cars are not, then the model can be trained to make the decision for the task at hand, okay? But these are the requirements. So if you just can't even define what is a good car and what is a bad car, and I don't need that, you cannot find 5 people, if you put them in the same room, they cannot agree on whether a car is good, beautiful or not. So that becomes a challenge for, especially supervised learning, because if you don't have enough training data, and if you don't have enough labels for that, then the training, this deep learning model will become a challenge.
Any questions here? I think then we can quickly get into security, and I don't know if you're running over time.
Yeah, there's some more similar thoughts. I mean, you got people in the chat, putting on their hacker hats and just thinking how they can break it and fool it. One kind of related it to, if you bring it something new it's never seen, make the boundaries change, then it's not going to know what to do with it, or the other comment was that's why the human brain can be fooled because of social engineering. So
Yep.
yeah, I think I kind of wanted to lean in towards the offensive side of things. Is like how can you fool this? How can you trick the model? I won't name vendor names, but we know a big machine learning vendor had an issue where someone was able to fool their model or kind of retrain that model to think bad is not bad anymore. And I'm curious of where those breakdowns happen with deep learning. What is deep learning susceptible to from that perspective? And
Sure. Yeah, I think that's very, very important. I think all ML, any AI model is always susceptible to attack. The question is what kind of attack and what does the attacker need to know? What information do they have, and how much data do they need to be able to attack it? I mean, these are all questions we'll get. We have a few slides and we can get into that. Do we want to, Ali, should we start with that or just go through this first? What's your take?
I don't know how much time do we have. That's the question.
How much time do you have, Sheldon?
Yeah, Phil, do you have a preference on time? I mean, usually I know we go like an hour and a half, but it doesn't really matter.
No, they can as long as they need.
Yeah.
Okay, sounds good. Okay. So let me go through this stuff. You guys know very well. I don't want to spend too much time on it, but essentially, this is an example. We talk about there's new variants created every second. So we want to apply it deeply into problems where there's lots of new things happening where you can't remember all of them. Right. So if it's eternal blue, once I know the snort rule for it, then I'm done. Right. It's like, but if it's some new kind of phishing document, zip file, or DLL or file list, or something that it's changing all the time. That's very hard to capture in any kind of rule framework, because you can just change a few bytes in the right places and fool that system, right? So that's really what we're trying to address. How do we defend against these kinds of things that change all the time? It could be the nature of a C2, or it could be the nature of how the payloads are created of different types. And so basically the goal we are talking about is, can we apply to network traffic analysis similar to image and speech? So instead of looking at pixels, I'm looking at PCAPs. Think of it like that. I have a bunch of data coming in. I'm extracting raw information from it. I'm extracting objects from it. And then I'm sending those floating point numbers, or whatever I extract from that stuff, I'm sending it to a deep learning model. It will do some calculations, and the end is going to tell me what it thinks that thing is. And this model has already been trained on, let's say, X number of years of data of the past, right? And the question is, when attackers change their methods, how many mistakes will it make? Obviously, it won't be perfect, but it's going to be 80%, it's going to be 90%, it's going to be 99%. Where is it going to land? And that's all a function of how much data has it learned from, and how good is this network? How large is it that it can encompass the future mutations that people are doing? One example is, there was in 2019, there were a couple of new privilege escalation CVEs that came out. And so the specific, POC code in GitHub, it's very specific. It does the buffer overflow and, does something. But then the code you write around it, which will actually be, do the persistence, maybe delete things, hide itself. Everything can't be made perfectly new and made to look benign. And that's where deep learning systems excel. They can learn from all the patterns of the past attackers and how they structure their code, what do they use, and learn all these variations, even if it's not seen that specific attack in its past data as well, right? And here's an example. We've been tracking the Emotet family of malware, for over a year, for example. And what is interesting is these categories. By categories, we mean it looks like a cluster or a different thing to the deep learning model, right? So this looks fundamentally different from the previous, sample that they were using. And what you see is, over time, people, they use one sample and maybe people are starting to block it. They have the signatures. Then they try this one, maybe it didn't work very well. They went to the other one. Then they found a new, type of sample. Maybe it's a new technique. Maybe they compile something new. Maybe they use a different, library inside it. And then that goes for some time. Then they again flip it to another one, right? So basically, as defenders start adding signatures for these things start changing. And sometimes they actually come back. Okay, now I've gone here. At this point, the firewalls and other things would have say, oh, this signature is too old. I can't keep memory for all of them. So let me get rid of these old signatures. So now they go back to the, the old sample, old style that they were doing before, right? And so this is a typical attacker behavior or mutation where they keep trying to change to defeat what is trying to detect them, right? And the essential question is like, I have to make what I look like change over time. And then for a signature-based system, it's really clear, do you have the signature or don't? Or if you have a Yara rule, is it expressive enough to figure out this new sample or not? Versus a deep learning system where, can it generalize to this new sample? So we talked about that boundary of data. When you have this new data coming in, so here's a good example. If you if I take the colors out, so on the left side, blue are benign samples, yellow is malicious, red is the emotet, right? If I take, and these are just some, some features about, what are the code and, imports and what are the things that it's using in the malware. If I take out the colors, it's very hard to say, what is good and bad, right? It's even with the colors, some of these things interleave. You could have some hack tools or some, drivers that look like malware. So it's not an easy problem to separate these things out. Whereas what deep learning does is it takes all of these samples feature space, and in the hidden layers, it separates them out, by using those matrix multiplications, such that it's separating the data out so we can draw a boundary. So now, if you look at the yellow, these are all the known militias that we have trained with. All the emoted is somewhat like them, but some of them are very different. The ones here are not like all the other, they're very different from the existing samples. And the benigns, these are pretty different. These could be like Firefox or Chrome or any other Linux library, for example. And here you notice this is a region where you can get confused, right? Here, some blue things look like bad. Some bad things are starting to look benign because they probably, added a bunch of things to make themselves look benign. So this is where it's important to be able to draw a good decision boundary between good and bad. And so when a new sample comes in this space, I think it'll be good to show this video of how a neural network learns. So this is, how you start with. This is the input data. You don't, the layers haven't been added yet. So all of this stuff is clumped together. The benign, the ransomware, crypto miner, these are just the raw. This is like what a sandbox signature system or a basic ML system would see. And what deep learning does is in each layer, it's trying to separate the data out. It's trying to represent it in a way that they are separated such that it can draw a decision boundary. So now you can see in this, three-dimensional space, we've dumped it down to 3 dimensions, actually multi-dimensional. You can see that the blue stuff is very separated from the rest of the system. Right? These are in different categories of bad things. And so I can possibly draw a boundary, 3D boundary between these shapes. And when a new thing comes in, so in the last step, you have trained this neural network. Now you're applying, new malware over here. It's some, it's not just like the ones in the past. It's different. It's in this space here. So it's not like the stuff you've seen before. It's a new sample. But because it's drawn this boundary between what it knows is good and bad, it's able to place it in the right space. So it's basically to say this is definitely malicious and not benign. And that's giving you an intuition. This is just a representation in 3D space. In reality, machine learning things in hundreds of, thousands of dimensions, but that gives you a sense of it's able to separate the data to tell good from bad. And when new things come in, it's the only way to really defeat it is to have enough of the goodness in them and not do anything bad. At that point, it becomes good, right? So you have to do bad stuff and your code has to execute those things without looking like that. And which is a much harder bar than changing a signature or defeating a Yara rule or doing those kinds of things. And that's where the bar is changing. And Ali, do you want to talk about, there's a real example of an attack that we saw in the Middle East on some oil and gas companies. Ali, you want to discuss this quickly?
Yeah, so just to put a little more light on these graphs that you see. So basically what happens is that the task of the deep learning is to find the perfect representation for the task that we want to do. So at this time, the task is exactly, thank you, Saumitra. The task is to separate benign and malicious from each other. And then as an addition, we want to separate even the categories and types of malicious from each other. So that's what the deep learning is trained to do, okay? To have an intuition, if you are looking at two objects head on, okay, while one of them is actually hidden behind the one that is close to you, you can barely see the one behind. And in your opinion, these two things are exactly the same. They have no separation from each other. They are on the same line and they are similar. But when you start to moving around those objects, then you see the separation between them, okay? Just assume that two items are put a feet apart from each other, but you are looking at them head on. They are close to each other in your perspective. But when you start to move around, you see the separation between them. That's exactly what's happening here. So on the left side, you see things head on, okay? That's how it's being represented in a raw way. And that's how the attackers are trying to put things behind each other so they look benign. They look, the malicious behavior is hidden. What deep learning is doing is actually turning the space in a way that these things are being separated from each other. And it finds the perfect representation for you to see the difference between these items. And that's how you get to the item on the right, okay? So these are the same points, exactly the same points. What has changed is the representation in the space. And this is a 2D projection just for a presentation. In reality, This is hundreds of thousands of dimensions. So to answer that question about the matrix representation, we should be able to use the matrix evaluation because we want to show hundreds of thousands of dimensions, okay, not just 1 and 2, and that's why we use matrices. The other one is that if about the comment that is being made that it can be fooled because it forgets about things that it sees in the past. It doesn't want to remember them. It doesn't need to remember them. What it learns is the perfect representation of the space. So whatever you throw at it, what it does is that it gets it from this representation, project it into the new representation. And what the training has done is to make that new representation in a way that all the bad things are grouped together on one side and the good things are grouped together on the other side. And that's how you are able to see the separation. Okay.
And that doesn't mean you won't make a mistake. Like, look at this yellow sample here. Did you see this one here? This is going to be a mistake. Most likely, it's going to be very hard to separate this, most likely, right? So, all machine learning, deep learning makes mistakes. In fact, I was talking to some friends at other companies who, if you don't make a mistake, you're not trying hard enough, right? So it's important. You could miss most of the things and not make a mistake and not have false alerts. But once you try to do prediction, you will make a few mistakes. The question is, how many mistakes are you making, and are you learning from the mistakes? So a key important part of deep learning is, and one thing we've looked at is, if you make this mistake and a user or a domain expert like you folks see it, what can you do? How can you make the system learn? You can say, hey, you guys missed this. Not you guys, I mean, you as a model missed this. If you mark it, what does it do? So we have a very interesting workflow about when a mistake is marked either by the threat analyst or, later on somebody, some consensus was reached in the community that this was bad and nobody saw it in the beginning. How do you learn from that mistake? That's another piece of, you can change your weights, you can add layers, you can then try to correct the mistake. So it's not that it's perfect, but it starts with fewer mistakes. And when it makes a mistake, you can tell it, hey, this is a mistake you made, and you can try to learn from that. And that's very important part of having an AI model, that it has to have the user tell it when it's wrong. Otherwise, it cannot improve. It's not that it's going to be a black box and it's perfect on day one, but it has to be usable. It can't be like making 20% mistakes.
So a couple kind of comments and questions along this line. One says, if I as a hacker have access to the model, can I use some sort of optimization algorithm to automatically make my malware undetectable? I just basically have to take small steps towards the quote unquote good area. And then the other comment said, so I just need to pollute its representation.
Both of the comments are very good comments, very nice comments. For the first one, we have on a slide exactly this one. Okay. So this, what you just described.
And by the way, this is something we're actually talking to a lot of interest in our government and all about these kinds of things. So it's actually a very interesting area, because in the future, when nobody's using signatures, all the attacks will be done, and it's already happening in computer vision. There was an article from the U.S. Air Force recently. People are trying to fool the computer vision systems on drones by manipulating what it's looking at, like you said, by trying to find weak spots in the model. And Ali can talk about this. This is a very interesting area of how to defend against malicious AI.
So it's basically this discussion of adversarial attacks against the deep learning models, and that's take advantage of exactly the process that was used to train the model. That step-by-step process that I just described. This thing actually try to take advantage of it and start to find the samples that are closing to this boundary. Look at the blue samples the blue X that you see on the graph, okay? And start to modify them just a tiny bit in order to be able to move them over the decision boundary to the other side, okay? Basically, what they try to do is that to modify them such that from the oracle perspective, if it's an image from the human perspective or from the malware perspective, it still maintains its malicious behavior and it still maintains its ability to run, okay? But it moves to the other side of the boundary where the model misses it. However, this is exactly where it becomes challenging from the network security and from the malware perspective. You have to have all kind of this limitation. If you want to modify malware so the model misses that, you have to maintain the malicious behavior, okay? It's a game, you have to win something, okay? If you just drop your malicious behavior or just disable them, well, that thing it actually became benign and the model hasn't made a mistake. The other thing is that to make sure that it keeps its ability to run, Okay, so a lot of times when you are actually training these kind of attacks on the machine learning models, the sample that you started with loses the ability to run, okay, or it becomes so, stripped out or modified, so it cannot perform that malicious behavior that is expected from. So there are lots of constraints over there, and which makes the task of the attacker much harder. Okay, and it is but however, there are mechanisms actually to defend against these things. Okay, there is another thing comment that was mentioned that, oh, so all I have to do is to pollute the new representation. You cannot pollute the representation, because this is what is being learned during the training. What you can pollute is you can pollute the training data. If you can inject your wrong data, wrongly labeled data into the training process, okay, and the model is trained based on that, then the representation may not be as perfect as expected, and then there would be blind spots. That's why.
But to do that, we'd have to compromise your training systems that you're using, right? I mean, we couldn't do that from a particular endpoint that's running your,
Right. Unless we blindly trusted the input. So one thing could be, if the analyst said, hey, you said this was bad, but it's actually good, and we just take that input without thinking, automatically, then we could, we would end up polluting our system. So that's why we have this thing about whenever a mistake is made in the field, let's say, there's a SOC analyst somewhere, he said, hey, this was an FP or this was an FN. It is actually triangulated by our SOC team. We have a threat analyst, and they will actually give the final verdict. So the model will only train from mistakes that have been validated. It's not enough for somebody to just, otherwise you're right, you could have this polluting attack where if somebody's just biasing it, you'll just learn from that and you create this problem. Very important, very interesting point.
And the last thing that you can see in this slide is that another way to thwart this kind of attack is that by having a combination of the models to make a decision, and then you combine that. Yes, you can fool one model, okay, and jump from one side of the boundary to the other side. But if you employ multiple models, we call it ensemble of the models, okay, then it's very hard for you to fool them all together. It's actually exponentially harder, okay, because then you have to cross the boundaries of all of those models with the same
time,
making the same modification, okay, which makes it exponentially harder. Any of you guys who have remember your probability classes, this is basically 1 minus p to the power of n, and n is the number of ensembles. It keeps exponentially increasing, and that makes it much harder and much harder in order for you to have a successful sample that can run, be malicious, and evade all these models over there. So yes, adversarial attacks are real things. It is possible. It's theoretically possible, and we are actually working on this kind of things. There are defenses against that, both in training time and evaluation time, and it's actually an interesting, war game between the attackers who are using deep learning and the defenders who are using deep learning in order to defend against them. Okay, so the game has changed.
Yeah, because the follow-up comment, the follow-up comment was, but that means the learning stops at some point. So an unknown new thing can fool it, but if it's always learning and adjusting to the new things, then it can be polluted.
Saumitra, can you go to the previous slide? There you go. No.
Is it this one?
Yes. So this is exactly the situation as you mentioned. Okay, so as we mentioned, one of the key advantage of the deep learning model is the ability of generalization. Basically, it learns from things, and that learning can expand to the things that it hasn't seen. Okay, so this is a real example. This is an Ottawa ransomware. Okay. So it was detected around, January timeline of 2019. And this is actually the graph that you can see from how the industry reacted to that, okay? So by the time that it gets actually into the virus total, which means that somebody actually found it, it's already been in the wild, somebody send it up and say, hey, this thing looks very suspicious, okay? Very small number of vendors actually were able to detect it. And it took them the whole day until they start to react to this thing. And then it took them another 3 days, so they have a good conclusion that this thing is actually malicious, okay? So 4 days a ransomware was lurking around and can potentially infect a lot of machines and cause a lot of damage, okay? So
and this normally happens when it's in the press or some bleeping, somebody wrote about it, it's on some Twitter feed. That's when this has happened, right?
Yeah. By this time, this thing has been at least in a while for a few days or even more. Okay, we have seen samples that these things were lurking around for months and nobody detected them until somebody put it there. 3 days later, everybody detects it. Okay, yes, but what happens so far? Where were you? Okay, so however, if you Saumitra, if you give me the banner, you
Which
remove.
one?
No, there is a there was supposed to be a banner underneath this. Okay,
Oh yeah,
so
that's okay.
yeah, one thing we have done is that we evaluated this model. Obviously, when we saw the samples, the state-of-the-art model that we have automatically caught this. Okay, and we say, hey, well, this is good. We can detect it. One thing that we have done is that we went back in time by evaluating that sample with models that we trained 6 months before. Okay, there was no way that we could have seen this sample. This is a new ransomware. This was completely new thing. Okay. And when we were training the model, the training data did not have any of that information. And that model also managed to catch this thing, okay? Because it's not zeroing down on the representation, on the exact signature of this kind of ransomware. It learns and it projects this sample into that representation, as I mentioned. And this sample gets close to other ransomware, to other malicious samples that is out there. Not only we managed to detect it, we also managed to call it as a ransomware. That means that we have very accurate mapping between this particular sample and what is happening over there. Okay, so that's the
and remember, the deep learning is looking at all the bits and bytes, and it's not looking at things that humans may look at always. So it's not saying, hey, is there a packer, or it's looking at these counterintuitive features and their combination. And that's why for the attacker, they have to know what it's looking at. And by definition, we don't tell the deep learning what to look for. And that's one reason that it makes it harder to, move the decision in a certain way. The only way to really do it is to have access to the model and send millions of samples and systematically figure out what might be a weak spot. And that's always hard. You have
even that is a exponentially difficult challenge.
Yeah, and I always had like this attack was in the Middle East, in one of the largest oil companies in the world. We got these samples, so these are the existing samples that they had seen in the last year in their SOC team, and these were the new samples. So it's not like they're like the others, but they're close enough, and we could. So the decision boundary was somewhere else. So the attackers definitely made it very different from what they had. And these are not in VirusTool or anywhere else. They're just with the company itself. But it is far enough away from the current threads that they had seen that it's new. Clearly, it's not in any signature database. But then because of how the machine learning is generalized, it's not able to do this, right? To do this is much harder because most people are focusing right now on defeating signatures and getting in and defeating Yara rules and things like that. Whereas to defeat this, it's not that it cannot be done. It increases the bar of the attacker much higher, and it requires them to have much more intimate knowledge of what are you actually looking at. For us, for example, we don't, everything we have is encrypted. It's all double obfuscated. It's very hard unless they get in and steal the secrets. It's hard for them to actually figure out what the model is looking at. And doing a black box attack, which is, I don't know what it is. It's a black box. Let me try different things. It's going to be exponentially hard. If you have access to data on the inside, you could potentially find weak spots. But again, there are ways to get away from that as well by employing ensembles of models or by perturbing the input. One of the interesting things people do is in self-driving cars, they take a stop sign and they put some sticker on it, and they found one weak spot in some model to make, they think it's not a stop sign anymore. But these are very specific toy examples, and you can make sure you perturb. You can take the input and add some random noise, so you don't hit those, some blind spot in a model which will go and trigger those alerts. So these are known things that can be done to machine learning, and there are also interesting defenses coming up against it. I think what will be interesting in the future is if two fully capable deep learning models, one is generating malware and one is trying to defend, they can also learn from each other. We've even tried that where we generate things and we see if it will defeat ourselves, and we can actually make a defender learn from that attack as well, which is another interesting aspect that I think there's this whole area of generative adversarial networks in computer vision, where you try to defeat yourself before you go and put it in production. And that can also help you defend against some of the attacks. Doesn't mean you can't be attacked and you won't be fooled, but this really increases the bar on the attacker to, to what they have to do to get in. It's actually very interesting. We've actually taken, I don't want to name any vendor, we've taken boxes from any of the big guys just to see, okay, if we presented this to an attacker AI and it tries to automatically generate things, will it systematically find a way over many iterations to see, oh, this is the style I need. And it's pretty interesting as to, how it's able to do that. And it finds, with enough iterations, it can find at least things that are signature based or rule based. It's able to find those weaknesses in the rules, but finding a weakness in a model is harder. It's not impossible, but it's much harder. That's really what we're looking at.
The objective is to make the attacker's life as hard as possible. That's what the security is all about. And these things, maths are on our side to do it.
Yeah, I mean, and that's what I'm saying. So, like, I remember Qualcomm used to say, hey, if someone wants an iPhone exploit and they're willing to pay $1 million, they'll find it. I mean, it's a matter of what is the cost and how much are people willing to pay. So it's really of increasing the cost and burden on the attacker to make it, okay, it has to become like a nation state coordinated thing to really find that and find that gap potentially. So that's the kind of, you're really raising the bar that it's not easy to do it. You really have to be motivated, financially backed, and doing these kinds of things.
There was a question. Someone said, I can understand if you can't answer, but are these detections from active anti-threat systems?
I'm not sure if I understand what is active anti-threat system means, but these are exactly the models that we train.
Yeah, I'm not either. If they wanted to clarify, they can. But yeah, I'm assuming some of the models that y'all were discussing off of earlier, some of the malicious models, if they're from anti-threat systems.
Yeah, everything we train on are real samples on the Y. So they are 10, 20 years of data.
Everything is real. Every one of these things that you see are real samples, are real data, everything.
Okay, cool. Hopefully that answers the question, but if not, feel free to clarify in the chat. And I'll share
and that shows the variation, right? Like, attackers are pretty, they try to, I mean, if you notice that people use Golang, then they use RTF file, then people are using XLS4 macros. So it's not like they don't change. They keep changing techniques and styles, but if your model has learned something more general from raw, so you're not stuck on if this, then do that, then it's much more resilient to these kinds of changes. Doesn't mean it can't be fooled, but it's much more resilient than doing any of the other things. Because we've noticed for most signature based, we've actually built attacker AI just to see, how it works. And, they can they can bring a detection rates down a little bit, but for signature based perimeter system, it's very, at some point they find a way to bypass. They find a systematic way. Oh, this is what I need to change, and it'll always get through. Right, so that's one of the things that is you need. Once attackers start using some of this automation, you will need on the defense side. And we're already seeing that in for example, in phishing, there are some phishing emails now being generated by AI where they make it sound more and more human. And that there are now fake news blogs that are generated by AI that a human can't tell if it's real, if it's written by a human or not. Right. Similarly, they're writing emails, and these business email compromise. These things are getting better. They can be more. If you think about chatbots, they're making a conversation. People can even think about a series of conversations. At which point, credential phishing or something will happen. That's one area that's happening. Clearly, we know there's automation in the malware. One of the interesting things we've seen recently is some of these malware families actually have an ML model to detect that they're running in a sandbox. So they actually look at the OS. They get some, feature. They could get the CPUs and templates. They could ask the OS about what it is, and then they have a model to predict, is this real or am I running in a sandbox right now where the attacker is defender is trying to detect me. And so these guys, we've actually seen, interestingly, can use ML to figure out where are they running. They don't have to write a rule like, hey, are there real photos here? Is the CPU clock correct? Is this a VM or a hardware? What is it? They can again take features from the underlying place they're running and then make a decision as to is this sandbox or not. And then if it's not a sandbox, they don't run. And then we've seen these kind of things. For example, even in malicious applications on phones, they would check, which operator is this? Where am I right now? Is this a real SIM card or it's like a fake sandbox machine, Google Bouncer or something? And then it would take a lot of pains before doing anything malicious. It's really going to figure out if it's really running in a real user environment, right? So attackers can use AI not just to make samples from scratch. Like we saw, remember, it's making faces from examples. Clearly, they can take existing pieces of code and mutate them in interesting ways. Right now, the way people mutate it, they put a bunch of no ops, they add unnecessary libraries, they just change the code around to change all the change the imp hash or change the hash or whatever they want to do. But this can do more fancy things about putting the code blocks together to achieve the malicious behavior, but be very different from a signature perspective. And so it'll be interesting to see over time what happens as more and more defense systems use machine learning, deep learning, how the attackers are going to have to evolve. But this is like the Windows Mac thing, right? Unless there are enough AI out there defending, they don't need to they can just go after the signature-based systems and get in. And for now, once there's enough, then you'll see them doing much more targeted things like this.
As we get better, they become more sophisticated.
Yeah. I think that's all we had, but clearly we can talk about, we can take questions or other things. I hope this was interesting to people and piqued their interest.
Yeah, it was great. We kept making jokes in the chat about our neurons were hurting. So much information, but this is my preference way of learning is by fire hose. So I definitely enjoyed it, and I appreciate you guys sharing. If anybody has any questions, you can throw them in Q&A or in the chat. We can hang out for a little bit. You guys, I think we hit close to the 2-hour mark nearly. I forgot exactly when we started, but really good stuff. And this will be posted later on YouTube on the channel. So if you need to go back and digest some of this information, awesome. While there may be questions coming in, I'll give some time. Do you guys have information on, where they can contact you all, find you, answer questions? Are you on Twitter? What's kind of your preferred way
I'm
of
on Twitter. I'm on Twitter, I'm on LinkedIn, or you can just do Saumitra at bluehexagon.ai. That's good too. But LinkedIn, Twitter is good as well.
LinkedIn is good. Again, Saumitra, and my name is Ali at Blue Hexagon. We would be happy to answer any questions.
Yeah, or you could ask you guys and you can forward it also.
Yeah, definitely. You can channel through us as well.
Yeah, and it's sort of interesting. We're seeing, like, if you look at some of the large financials and all, people are using deep learning a lot for fraud detection. They also use deep learning for deciding when to give someone a loan. So now there's this whole area of, like, is your AI going to be biased against people? So you have to make sure you don't have bias and those kind of things when you make decisions. So it's actually interesting. So you have to start introspecting your models as well to make sure they're not making decisions for the wrong reasons and discriminating against people at this point. So the DL is being used in so many different places, and I think both in security and in some of these places where they make important decisions, you need to be able to say why you made a decision. So at RSA this year, we did announce this explainable AI. So we try to explain the model's decision as much as possible. Obviously, you can't, dissect the model. The whole point of deep learning is hard to dissect it to a specific rule. But you can basically give a sense of what are the different tactics that were employed that chose the model to decide a certain way. And this is the same issue that happens when you do mortgage loan decisions. You have to explain, why did you choose to deny this loan and why not, right? So this model introspection and explanation is another interesting area that's important for AI. And then the same thing for car. If a car went and crashed somewhere, we need to figure out why did it crash? What was the reason? What drove it to do that? And so that's another challenging area of deep learning. That while it's the most effective thing, sometimes it's hard to explain why it made a decision. And so that's another active area of research right now on figuring that out, how best to explain the decision that we've been working on also.
I think you guys answered kind of most of the questions I was thinking about. Is like, how do you break the model? Can you break the model? What are the ways to do so? So you win a lot of that. And then I'm thinking, how can attackers leverage, machine learning, deep learning to make themselves better? I think it's kind of harder for them to collect data in some instances about, their opponents, if you will.
Yeah, exactly. Yeah. And then it's not binary. It's not binary like a signature. If you take any firewall, it either gets through or not, and then you can try to find patterns that make it or not. Whereas this is making probabilistic decisions, so you have to really understand why it's made the decision.
Yeah, because there's definitely stuff out there like this is a little bit lower level, but think like Microsoft's AMSI, their anti-malware, script language or whatever it is, but or script inspection. You have people that are trying to just go through and do just slight levels of obfuscation, change things here, and just slowly tweaking it. They do it all offline, but they slowly figure out how they can defeat AMSI on a particular system. So I guess it comes down to, can the attacker get hands on the type of detection software? Can they get their hands on some of these top enterprise or open source detection engines and run a lot of this offline and learn how to defeat it? It'd be curious to get in their heads and their world and see if they're leveraging a lot of this cool stuff.
Yeah. I think the question, it also comes to the question of, is it worth their time? At some point, if all the defenders are in that mode from, any of all the vendors, everyone has something like that, then there's enough incentive to invest in that. Until then, if I was the attacker, I would probably say, hey, let me just if I can get through most of the systems with small tweaks, then I shouldn't waste my time. I should first do that, and then eventually I think this will happen. That's my feeling. But clearly in the end, it is going to be that way, because no matter what you do, it's hard you can't remember all the signatures of the past. It's almost impossible. Right.
Yeah.
So, I mean, I've seen that just just calculating the SHA or MD5 of things going on the wire and matching it against a long list, you can't keep up with the gigabits in the network, for example. So it's, not possible. That's why you notice all these, you have signatures tuned for healthcare or finance or retail. So, everyone has to reduce the size somehow by making it targeted, right? And that means you're going to miss things that are old and you'll miss things that are not from your sector. So there's all these kinds of trade-offs you have to make when you try to remember everything with signatures.
Kind of on the defense side of things, there's just something that was run through my head for the last few minutes or so, was just on this defense aspect. I know you guys do network, detection and do integrations for prevention, things of that nature. But, as things have changed during COVID, right, you have a lot of decentralization of assets everywhere, right? It's you can't really tap into the network connection for all your decentralized assets now. And so those that invested in host-based, type of defense, right, that's all cloud-based and detached a lot, are kind of winning out here. And I think about, I was curious if you guys have seen stuff that's kind of more host-based smart detections and prevention. You have like the CrowdStrikes and the in-games and the Carbon Blacks of the world collecting network telemetry data as well. I mean, they're not collecting, I can't talk. They're not collecting like Zeek level data necessarily on their data sets, but they are collecting network information at the endpoint. I'm kind of wondering how many of those are moving into using machine learning and deep learning for, prevention of stuff that they're seeing at
I think
network, on the endpoint.
I think they're doing a lot. I mean, the endpoint guys have already invested in this, but they have, even at Qualcomm, we used to work on stuff like this. One of the challenges we had was the resources we can allocate to ML and how good of a model can we put there. You can definitely do better than signature-based systems, as we've seen. That's how they came in and took business from the existing EPP vendors, right? They came in and said, you had the Silence tool, unbelievable tool, and things like that. So clearly that was a step above what EPP was doing. But in the network, now what's happening with the fileless attacks is, they're trying to avoid writing to the disk, or the first thing they do is they try to disable the agent. One of the things interesting in the cloud that's happened, a lot of people are moving to the cloud. You actually may not even have instances. You might have services or Lambdas where you can't put anything on that, on the serverless stuff. So then, and also what is interesting is we worked with AWS and GCP. They just announced packet mirroring. In fact, we just deployed at a customer recently, 3 appliances, 200 different instances mirrored. It took 5 minutes because of all the automation. So the cloud also makes it very easy to install these things once the traffic mirroring is in place. I think that investment is being made by Azure, GCP, and Amazon as well. I think once you have traffic mirroring available in the cloud, then people will inspect traffic there, because you can't, a lot of the DevOps guys I talk to, they don't like to put agents in all their workloads. They slow things down. So that's one aspect over there. For really the road warriors, you could have a cloud firewall with these Zscaler style, or you could have put an agent, or you could be bringing some traffic back on-prem and inspecting there. And another interesting place we are thinking about is, you want to protect the user, you want to protect the data and what they operate on. So if you have all the data residing in SaaS and the malware and stuff is there, you maybe want to protect the data itself. You don't care where the user is coming from, what they're doing. So, the deep learning engine can also be applied because it's very quick. It can be applied to scale for SaaS applications as well, by looking at all the objects people are sharing on Slack or OneDrive or whatnot. So that's another place where we are taking our engine as well. So basically, as long as you can get to the network and the data that people are computing on, then, eventually, if you think about it, people also have this thin client Chromebook. At some point, it's possible that some of the large banks, they actually, they re-image their laptops every day. So the endpoint doesn't really have anything much. So then it becomes about protecting the data that they're operating on. So there could be very different, interesting models of where you need to protect things. But clearly, this move to the cloud and decentralization and there's many perimeters. You need to be able to install, whatever AI model you choose in those places where the data is being accessed and traffic is coming. And that's going to be key. With more and more APIs and automation, that's going to become, the way we deploy these things is going to become interesting.
Yeah. Well, man, really excellent stuff. I could sit here and talk to you guys for hours, and we've kept surprisingly a decent attendance. We've had some drop off over time, but nearly 2 hours, or not right at 2 hours.
Yeah, it's a lot. Yeah, it's
Really good
gone to
stuff.
18.
And we really appreciate your time. I know y'all have your own families and everything to attend to. It's y'all on a different time zone as well, but I really appreciate it. I think we can probably kill our stream recording, and if y'all want to hang out for a few more minutes and chat, but no more questions came in. So I think we're concluded. I really appreciate it.
Sounds good. Thank you all for all the
Thanks,
questions.
gentlemen.
Very, very